Okay, we got more circle stuff to deal with. And this we're going to call Circles 102. So let's go right to it. This talks about segments within a circle. So what segments are we talking about? Well, we have tangent lines, we have tangent segments, we have secant lines, we have secant segments, we have external secant segments, we have internal secant segments, we have whole secant segments. What are all these things? Well, a tangent line is just a line that intersects a circle at only one point, called the point of tangency. A line that intersects a circle at only one point. So it's kind of like a line that bumps off the edge of a circle. Now, a tangent segment is just a portion of a tangent from that point of tangency to some point outside the circle, beyond it, okay? This goes on beyond it. So that's a tangent segment. A secant line is a line that intersects at two distinct locations. Two distinct locations. So a secant line is a line that intersects a circle at two places. Now, we got different types here. A secant segment is a portion of a secant line with at least one point on the circle. At least one point on the circle. Now, we've got three types here. The first one is the external secant segment, and that's from a point on the circle to a point outside the circle. Secant segment, outside. Okay? We have an internal one. Well, that's actually just a chord. The internal secant segment is just a chord that happens to be part of this whole line. And then you have your whole secant segment, which is from that point outside through the point on the circle where the two of them meet all the way to the far side. So that's the whole thing. You're going to have to understand these parts of these segments, because what's going to happen is this circle does neat things with these segments. So let's start with a diameter to chord theorem. A diameter is perpendicular to a chord if and only if it bisects the chord and its arc. So in this particular case, my A and B are in the wrong locations. This diameter in the black line will bisect my arc AB if and only if it cuts it in half, it's perpendicular, and it cuts the arc in half. It has to do all of that. So what is the length of the radius if the diameter is perpendicular to a chord that is 8 inches long and 6 inches from the center of the circle? What is the length of the radius if the diameter is perpendicular to a chord that is 8 inches long and 6 inches from the center of the circle? Well, if I think about this here all together, I know that I got to go from C out to the intersection point has to be 6, and from A to B it's 8. But if this diameter cuts that in half, that means from A to that intersection point is 4. So then what I could do is use Pythagorean theorem, say 4 squared plus 6 squared has to equal the radius squared. So I got 16 plus 36, which gives me the square root of 52. So in this case, the length of the radius is the square root of 52. Neat little problem there. So that's what I was looking for, is that radius. And you can see the right triangle. Okay, now two inner chords intersect. Theorem. Excuse me. If two chords intersect inside a circle, then the chord divides each other such that the product of each portion of one chord is equal to the product of the portions of the other chord. Kind of a confusing little theorem there, but what it's saying, okay, I got two chords that are intersecting each other, and they're doing it not at the center point, or they could do it at the center point also. So in this case here, I got chord GB that's intersecting chord EF, and they're intersecting at this point A. So what this theorem tells me is that from A to B and A to G, if I multiply those two values, I get the same result as if I multiply A to E and A to F. Those always work out. Okay, now, tangent line theorem. Tangent lines are perpendicular to a radius at the point of tangency. So there's a radius that goes from C out to the circle right where that tangent line hits, and when that happens, it creates a 90-degree angle with the tangent line. A tangent line will always be perpendicular to the radius of a circle. And again, if I draw in the external secant segment all the way out to point A, and I start with point C, what is the length of a tangent segment, that's the outside part, given that AC is 13 and BC is 5? Well, since it's perpendicular, that must mean I get to use the right triangle stuff again. AC is my hypotenuse, BC is a side, AB is a side. So AB squared plus BC squared has to equal AC squared. So something squared plus 5 squared has to equal 13 squared. Hey, go back to our triples. AC must be 12. Sorry, AB must be 12, because 5, 12, and 13 is a triple. But that's the type of problem you're going to see with this. Tangent line converse theorem, this goes the opposite way. It says if a line is perpendicular to a radius at its endpoint on the circle. So if a line is perpendicular to the radius where the radius hits the circle, well, that line must be a tangent line. It's just the opposite of this tangent line theorem. That's why it's called the converse theorem. Now, tangent segments theorem. Two tangent segments to the same circle from an exterior point are congruent. So if I start out here at point A, and I draw a tangent line to the circle and it happens to hit at D, and I draw a tangent line to the circle and it happens to hit at B, and I just look at the tangent segments from A to D and A to B, they have to be the same length. And that's because if I drew in AC, and I drew in BC, and I drew in DC, I could prove that those two triangles are congruent by leg angle. And because I'm doing it by leg angle, that means the whole triangles are congruent. So that means AB and AD have to be the same length. Neat little theorem there. Now, what is the length of tangent segment AD if AB is 13? Well, if AB is 13, AD has to be 13. That's the type of problem you're going to see. Secant segment theorem. If two secant segments intersect the same circle, then the circle divides the secant segments in such a manner that the product of one of the whole secant segments and its external secant segment is equal to the product of the whole secant segment and the external secant segment of the second secant. This one's a little harder to see, but allow me to see if I can highlight this a little bit for you. So, if I take the whole secant segment, A to G, and I multiply by just what's outside, A to F, I get the whole A to E times just what's outside, the A to B. That's what this is trying to tell us. So it tells me AG times AF has to equal AE times AB. The whole thing times what's outside has to equal the whole thing times what's outside. That's the thing to remember from this particular theorem. Now, a secant and a tangent happen to intersect, and we break it down. So if a secant segment and a tangent segment of the same circle intersect outside the circle, then the circle divides the segments in such a manner that the product of the whole secant segment and its external secant segment is equal to the square of the tangent segment. You got that? Let's see, where's my magic pencil? There we go. So, the whole thing here times the outside has to equal this whole thing times its outside. Oh, wait a minute. The whole thing and the outside are the same value. Well, isn't that rather interesting? So the whole times the outside has to equal the whole times the outside for our secant segments happens to match up to be the whole times the outside equals the whole tangent squared. So, what does that mean as far as our equations are concerned? The AG times AF, the whole times the outside, has to equal the whole AB times the outside, the AB. So whole times outside has to equal whole times outside. Remember that all the way through, and we're going to see these things work out. Okay. Thus ends circles 102. This is probably the toughest portion because those different theorems are about calculating length. We have to know those theorems. We will practice those theorems in the assignment. So, make sure you have those theorems down. Make sure you understand that if two chords intersect inside a circle, it's the two parts of the chord times the two parts of the chords. Those have to be equal. If it's a point that's outside, it's the whole times what's on the outside equals the whole times what's on the outside, whether it's a secant or whatever. And if it happens to be two tangents, they're the same. So thus ends Circles 102.